Welcome to our sixth lesson on electrostatics. We're going to be looking at the electric field today. Now our electric field symbol is a capital letter E, and the unit will in most cases be newtons per coulombs. Now note that newtons and coulombs are in capital letters. Later on you'll see you might also end up using volts per meter, just depending on the formula that you do make use of. Now one of the most common formulas that we will take a look at in this lesson is where my electric field is going to be equal to the force divided by the charge. And this is where my very first unit comes from, newtons, which is that for force, divided by the unit for charge, which is coulombs. Do take note, the electric field is a vector quantity, so apart from just the size or the magnitude, there will also be a direction which we'll need to indicate. Now the definition for electric field states that it's the electric force experienced per charge, or you can say per positive charge placed at a point. And this obviously is deduced from our formula that says electric field is equal to the force experienced per positive charge placed at a point. Now as said, our electric field is a vector quantity, so it's going to be having a direction as well. Now this direction is constant. It will always be in the following way. Now our direction always points away from a positive, but it will go towards a negative. So away from positive and towards negative, that is always going to be the direction for an electric field. Now let's first go and take a look at our individual positive and negative charge. Now they will experience this force per unit charge, which is then what we call the electric field. Now an electric field is pretty much the same as your magnetic field, which you've done in grade 10. And that means it's an area around the charge which you do not actually see, but where there are actually force lines in which that area, an electric field in this case, will be experienced. So let's say we start off with our positive charge. We will then experience somewhere in the region of this positive charge this electric field. And the direction, as we said, is away from a positive. So that means these field lines must then, with an arrow, point away from the positive. Now you would note that these electric field lines are drawn 90 degrees to the obstacle. They do not cross each other or touch each other. They just radiate out, in this case, from a circular positive charge. Now let's go and take a look at how the negative charge would look like. For my negative charge, they will also be radiating, but now our direction is towards the negative. So that means my electric field lines must be pointing towards my negative charge. Now it doesn't really matter how many field lines you draw. If it's though a very strong electric field, then there will be more field lines. If it's a weaker electric field, then there will be less electric field lines. But in most cases, as long as you would just go and draw about 4 to 5, if they did not specify it was a strong or weak electric field force, that will be sufficient. Now let's go and look at a situation where I'm going to have two of the same charges close together to each other. So that means in a close vicinity. Now we would still be having our field lines that will radiate out, but what's important is if I've got like charges, in this case two positives, they would actually repel each other. And we would need to show that repulsion using these electric field lines. So that means right here in the middle, these field lines won't just point straight out. Because there will be a repulsion, that means these things would like to move away from each other. That means that these field lines start out 90 degrees, but then they bend away from my other positive charge. And the same would happen on the positive charge as well, that the electric field lines would bend away here in the middle between the two. Now because it's positive, it means it must point away from my positive charge, all of these electric field lines as well as the bent lines, and you must note though that none of these electric field lines touch or cross each other. Now if we've got two negative charges, the same thing will happen. These charges do repel each other, so that means right in the center where these charges are brought closer together, there will be repulsion. The electric field lines will bend away, but note now the direction of the electric field lines is towards my negative. So all my arrows will then end up pointing towards my negative charges. But in the middle, they bend away. If I though have a positive and a negative charge that's in close vicinity to each other, then we'll end up with attraction between these two charges. And when we're going to take a look at attraction, they end up being a bit different than our repulsion at this point. So we'll still have our charges that radiate out, but if we're going to take a look at our electric field now between the positive and the negative, because it is going to be an attraction, they would actually like to move towards each other. So we will have our field lines between the two charges bending towards each other and actually making contact on the other side. Remember, it always points away from a positive, and you would note now, when I do this right here in the middle, it automatically also points then towards a negative, which is then my direction for my electric field line for my negative charges. So this is how attraction would look like. Now let's go and look at an example calculation that we need to be able to do. First off, they ask us to calculate the size of a force that's exerted on a charge of positive 3 nanocoulombs at a point in an electric field where the field intensity is 4,000 newtons per coulomb. So they want us to go and calculate the force, that means F, and they've given us the charge, which we're going to be using as a small letter q according to my formula. We'll just copy and paste it as it is in the formula, and they've given us the electric field intensity, that means our capital letter E. So we'll end up using capital letter E is equal to force divided by the charge. Now remember, they've given us a very small unit, which is Newton coulombs, and you must know your conversions again. So going from millicoulombs, let's say, to normal coulombs, then you'll multiply times 10 to the power negative 3, or you can divide by 1,000. If you have microcoulombs, you'll need to multiply by 10 to the power of negative 6. If you've got, in this case, like nanocoulombs, times 10 to the power of negative 9. And lastly, if it's picocoulombs, it's times 10 to the power of negative 12. So our formula starts off by saying that electric field is equal to force divided by charge. So if I want the force alone on the one side, then I'll go multiply out with the charge on this side, and that means I'll need to do the same on the other side as well. And once I've done that, my formula now changes, in this case, to being force equal to electric field times the charge. So we'll be having our value of 4,000 newtons times coulombs, or newtons per coulomb, multiply the charge of 3 times 10 to the power of negative 9. And this gives me a charge, or rather a force of 1,2 times 10 to the power of negative 5 newtons. Remember the question they told them it was positive 3 nanocoulombs? So for my direction, we know that our electric field always points away from a positive charge. So therefore, you'll just say away from the positive charge. Now the question which I would like you to go and attempt says, study the sketch below and answer the questions that will follow. Now they give you a sphere which has a negative 3 microcoulomb charge placed on insulating stands. And the question asks, draw an electric field pattern for the indicator charge, and if a point charge experiences an electric field strength of 1687500 newtons per coulomb, calculate the force experienced. So first pause your play and attempt the question before you're going to be looking at the answer.